You know, there is something deeply uncomfortable happening out there, and most people have no idea just how strange it really is. When astronomers first started measuring how fast distant galaxies were moving away from us, the expectation was simple. The universe blew apart in a big bang, things flew outward, and gravity has been pulling all of that stuff back ever since. Every physicist in the room would have agreed on that. Gravity slows things down. That is what gravity does. So the expansion rate of the universe should be getting smaller every year, every million years, every billion years. It should be decelerating, coasting toward a slower and slower crawl. Then in 1998, two completely independent teams of astronomers were doing the same measurement at the same time, and they both found something that nobody wanted to find. The expansion is not slowing down. It is speeding up. The universe is not coasting. It is accelerating, and not gently. Whatever is driving this acceleration is winning in a very convincing way over all the gravity of every galaxy and cluster and filament of matter that we can see. The two scientists who led those teams eventually won the Nobel Prize, but I suspect they spent several years before that prize came hoping they had made a mistake somewhere, because the result is just that unsettling. So let me explain what the measurement actually was and why it was so trustworthy, because this is the part people often skip. There is a particular kind of exploding star called a type I supernova. Now, when one of these things goes off, the physics of the explosion is extremely well understood, and the peak brightness is always very nearly the same. You get the standard candle. Every single one of these explosions lights up with roughly the same wattage. So if you see one that looks dimmer than another one, it is simply farther away. Distance and brightness are related by a very clean inverse square law. You go twice as far, you get 1/4 the light. So by measuring how bright these supernovae appear, you get the distance. And by measuring how much the light has been stretched red toward the longer wavelengths by the expansion of space itself during the journey, you get the recession velocity. Plot those two things against each other, and you read off how the expansion rate has changed over time. This is not a vague measurement. It is geometry and light. The answer came back. The distant supernovae were dimmer than they should have been for their redshift. They were farther away than the expected deceleration would have put them. Space between us and those explosions had stretched more than it should have. Something was pushing outward. Now here is where I want to slow down and make sure we understand what is actually happening physically, because there is a common confusion here. People hear that the universe is accelerating, and they picture galaxies like rockets with engines firing harder and harder. That is not quite the right picture. What is happening is that space itself is expanding. The galaxies are not flying through space. The space between them is growing. Think of bread dough with raisins pressed into it. The raisins do not move through the dough. The dough expands, and the raisins ride along and find themselves farther from each other. Now, if you press a spring into that dough before it rises, the spring is going to fight the expansion, try to pull the raisins back together. That spring is gravity. It works against the expansion. The question is what happens when you put something into the dough that does the opposite, something that causes the dough to rise faster the more it rises. That is essentially what we are seeing in the universe. And Einstein actually gave us room for this in his equations a long time ago, which is one of the remarkable things about this story. When he first wrote down the field equations of general relativity in 1915, he later added a term called the cosmological constant because at the time he believed the universe was static, neither expanding nor contracting, and he needed something to balance gravity. He called it his biggest blunder once Hubble showed that the universe was actually expanding, because the static universe was wrong and he had cluttered his equations with this extra term for no good reason. But now here we are, and his blunder turns out to be exactly the kind of thing we need to explain the acceleration. The cosmological constant is back, and this time it has data behind it. What the cosmological constant represents physically is vacuum energy, the energy of empty space. Now this is where things get genuinely strange, and I mean strange in a precise technical sense. In quantum mechanics, the vacuum is not nothing. It is a seething background of fields that cannot quite settle to zero because of the uncertainty principle. If you tried to say that a field was exactly zero everywhere, you would be specifying both its value and its rate of change with perfect precision, and the uncertainty principle says you cannot do that. So there are fluctuations. Virtual particles pop in and out of existence constantly. These fluctuations carry energy, and that energy is the vacuum energy. Now, the astonishing thing is that this vacuum energy should, according to quantum field theory, have a specific calculable value. When you actually run through the numbers, the theoretical prediction for vacuum energy is about 10 to the power of 120 times larger than what the cosmological constant actually appears to be based on the astronomical observations. That is not a small discrepancy. That is not a rounding error. That is the largest mismatch between theory and experiment in the history of physics. A factor of 1 followed by 120 zeros. So whatever is causing the acceleration of the universe, whether it really is vacuum energy or something else entirely, we do not understand why it has the value it has. The name we give to this mysterious something is dark energy. And I want to be honest with you about what that name means. It means we do not know what it is. We gave it a name so we could talk about it cleanly in papers and at conferences, but the name is not an explanation. It is a placeholder. Dark energy is simply whatever is responsible for the observations. It accounts for roughly 68% of the total energy content of the universe. Dark matter accounts for another 27%. Ordinary matter, all the stars and planets and gas clouds, and everything you have ever seen or touched or thought about, that adds up to about 5%. So we have a universe where we understand the ingredients well enough to give precise percentages, but we only actually know what 5% of those ingredients are. That takes a certain kind of courage to admit. Now, there is another way to think about dark energy that some physicists prefer, and it involves something called the equation of state. Every substance in physics has a relationship between its pressure and its energy density. For ordinary matter and radiation, more energy means more pressure, and that pressure contributes to gravitational attraction. But dark energy appears to have negative pressure. That sounds bizarre, and it is worth dwelling on what negative pressure means physically. Imagine you have a gas in a box. Ordinary gas pushes outward on the walls. It has positive pressure. Negative pressure would mean the substance is pulling inward on the walls, like it wants to be stretched rather than compressed. A stretched rubber band has something like negative pressure in the direction you are stretching it. Now, in general relativity, both energy density and pressure contribute to gravity. Positive pressure adds to the gravitational pull. Negative pressure, if large enough, subtracts from it and can actually flip the sign, producing a kind of gravitational repulsion. Dark energy appears to have negative pressure large enough in magnitude that its gravitational effect is repulsive rather than attractive. The universe is not just expanding, it is being pushed apart. What does this mean for the future? If dark energy is truly a constant, a fixed property of the vacuum, then the expansion will keep accelerating. Galaxies that are currently gravitationally bound together in clusters will stay bound, but the clusters themselves will recede from each other faster and faster. There is a quantity called the Hubble radius, which is the distance at which galaxies are receding from us at the speed of light. Anything beyond that radius is, in a very real sense, unreachable. Light from those galaxies can never catch up to us because the space between is growing faster than light can travel through it. As the acceleration continues, that radius will shrink over time. More and more of the universe will fall beyond our horizon. Billions of years from now, observers in the Milky Way will look out and see only the local group of galaxies. The vast observable universe we see today will have vanished beyond an expanding horizon. It will look to those future observers like the universe contains just a handful of galaxies, and there will be no way for them to know that once upon a time the sky was rich with 100 billion of them. There is an even more dramatic possibility if dark energy is not a constant, but is instead something that can grow stronger over time. Some models, called phantom energy models, allow for the energy density of whatever is driving the acceleration to actually increase as the universe expands. In these scenarios, the acceleration does not just continue, it runs away. The repulsive force gets stronger and stronger until it overwhelms not just the gravity between galaxy clusters, but the gravity inside individual galaxies, then the gravity and electromagnetic forces holding solar systems together, then the forces holding planets together, then the forces holding atoms together. In these models, every bound structure in the universe is eventually ripped apart in what physicists call the Big Rip. The whole universe tears itself to pieces in finite time. Now, this is a dramatic scenario, and it requires dark energy to have very specific properties. The current data does not conclusively require it, but it does not rule it out either. We simply do not know. What I find most interesting about all of this, and this is the thing that should really grab you, is not just that the universe is accelerating, but that the acceleration is so precisely tuned. If dark energy were much stronger than it is, the universe would have expanded so rapidly after the Big Bang that matter would never have clumped together to form galaxies or stars. Everything would have been blown apart before gravity could pull it into structure. If dark energy were zero or slightly repulsive, the expansion would have decelerated normally and eventually perhaps reversed. But the actual value is this extraordinarily small number, sitting at just the right level to allow a universe full of structure to exist for billions of years and then begin to accelerate. Whether that is a coincidence or a consequence of some deep principle we have not yet discovered is one of the most open questions in all of physics. There are several competing frameworks people are working on. One family of ideas says that dark energy is not truly constant, but is a field called quintessence, something like the Higgs field or the inflaton field that drove the early rapid expansion of the universe, a field that has a potential energy curve and evolves over time. In some of these models, dark energy was very small in the early universe and has been slowly growing, which might give us testable predictions about how the expansion rate should change in the future. Another approach says that general relativity itself breaks down at cosmological scales, that the equations of gravity that Einstein wrote down are simply not the right equations when applied to the universe as a whole over billions of light years, and what we observe as dark energy is really just our inability to correctly model gravity at those scales. A third family of ideas involves the anthropic argument and a landscape of possible universes, each with different values of the cosmological constant. But I will leave that one for another conversation because it involves some philosophy that needs its own careful treatment. The honest position right now is that we have a precise measurement of an effect, and we have no satisfying explanation for it. The cosmological constant fits the data. It fits beautifully, in fact, but it sits in the equations as a free parameter whose value we cannot derive from anything. That is not how physics is supposed to end. Good physics explains why a number has the value it has. The best we can currently do is say, the number appears to be this value because the universe has this value. That is circular. There is a lot of work left to do. The next generation of surveys, mapping billions of galaxies in 3 dimensions with exquisite precision, should be able to tell us whether dark energy is truly constant or whether it is slowly changing. A slowly changing dark energy would rule out the cosmological constant and push us towards something more dynamic, which would at least be a clue. A dark energy that looks constant to even greater precision would deepen the mystery. I think this is what makes physics at this level so genuinely interesting. You do an experiment, you get an answer, and the answer is not just a number. It is a number that does not fit, a number that points at a hole in everything you thought you understood. The universe is expanding faster than the laws of gravity say it should be able to. That sentence should not be possible to write. And yet there it is. The universe does not care what we think it should be allowed to do. It does what it does. And our job is to keep looking until we figure out why.